All right, so now we're taking a look at circuits, kind of interesting idea of circuits, and we'll get on to Euler circuits and then Euler paths and then Hamilton circuits and paths. So we have this definition up here, and instead of reading this out, let's just kind of break it down. This is just, we're getting to that point where now we're starting to look at, instead of like finite situations we can kind of like look at, we're looking at this idea that we could like, have kind of like always like this n+1 or this, additional piece we can add on and make this theorem that kind of applies to everything. We won't be making theorems for this, but we're proving them necessarily. We'll just be applying them. So in the graph to the right, I guess the biggest thing to talk about is that n is a positive integer, where n is the number of paths, the number of edges, essentially. So find a path with length 3. So where that means that our n is equal to 3 from vertex x to vertex y. And so let's hit pause for a second and see what that looks like. So if we wanted to find a path that, or if you want to hit pause and then come back to, that's fine. But if you want to hit a path that had a length of 3 that started at x and went to vertex y, what we'll be looking at is we'd be looking at an A, sorry, I got my pen, to B, so there's 2, and then to Y, and so that would be 3. So that's what this notation down here is saying, is that path would be denoted as x would be my starting point. I would go from x to A to B, and I would end at Y. And so that's what this is saying up here, is like, you're saying that you would have, these are the edges along the, these are the vertices along the way that you would hit, and the paths are just naturally listed in between those, or the edges, I should say. Something like this is called a circuit. A path from vertex U to vertex U is called a circuit. This is a circuit, the path that begins and ends at the same place. So we did not make a circuit. We just made a path. So a path versus a circuit. A circuit starts and ends at the same place, whereas a path is just going to get us through the particular vertices that we need to cover. So take a look at the next one. You want to hit pause and then come back, please do. So find a path of length 4 from vertex x to vertex y. All right, so some vertex x to vertex y. What our answers are saying is that, let's see if I can't get a color here. Here we go. So I start at x. They're saying go x to C, C to A, A to B, and B to Y. And so that would be a path once again, because it's not particularly a circuit, but we got our 4 pieces there. Perfect, we're good to go. All right, so next one is that we want to find a path of length 5 from x to y. So of length 5, they're saying that we have a couple different options. So we can start at x, we can go to A, my bad, this is clear. So we can start at x, we can go to A, then to C, then to start at x, go to A, then to C, then back to A, over to B, and then down to Y. So in this particular path, we're not worried about traveling on more than one. So we're not like going back and making the connection with the salesperson or the highway inspector. We're just trying to come up with this idea. They said that another way you could do this is very similar, is you could start at x, go to A, go back to x, go to C. Oop, we never actually went to, sorry about that. So start at x, go to A, back to x, back to A, and then B, and then Y. So the whole idea here is they want us to start at x, and they want us to end at y for each one of these. All right. So let me hit pause for a second and jump in the next slide. All right, so that takes us to our conversation about introducing Euler. And so just as a quick side note here, Leonard Euler was an extraordinary mathematician of the 18th century who did groundbreaking work in many different mathematical fields. And he's famous for the Königsberg puzzle. And that's just a famous puzzle where they had the city of Königsberg that wanted to try to figure out ways for them to do routes through the city, and they only had so many bridges, and they wanted to be able to pass on the bridges. So this idea of paths versus circuits and so forth. So Euler path is a graph, is a simple path that includes each edge of the graph, whereas an Euler circuit is a circuit that is an Euler path. So we already talked about circuits, meaning that we would never touch something more than once. We would start and end at the same location. All right. The degree of the vertex is the number of edges that are incident with V. And if we have a loop of V, then the loop is counted twice in the computing of the degree. And so if we have the loop, that means that's counting, that degree is 2 because that path, let me grab my pen. So like, if you remember what path looks like, so let's say this is X. So this would be a loop. So this has a degree of 2 because you have 1, 2. You have 2 different ways to go in there. That kind of seems weird, but because it seems like it would just be 1 degree, but it's a 2 degree in that situation. And then a graph is connected if each pair of vertices, V and W, there's a path from V of W. So it's kind of like adjacent in some ways. All right. Okay, so here we go, kind of looking at some examples of Euler. So determine whether path A, E6, C, E4, D, E5 is an Euler path from vertex A to vertex B. If it is not an Euler path, explain why. So let's take a look at it. So they're saying they want us to start at A, and they want us to travel on E6 down to C, and then on E4 over to D, and then on E5 up to A, and then on E6 down to C, and then on E3 to B. All right, and so the question would be is that a path from A to B? All right, so the answer is going to be false on that one, is because if you recall, to be an Euler path, you have to travel on each edge of the graph. All right, so each edge of the graph. So that one's going to be false. All right, so let's take a look at the next one. Let's go here. What did I just do? Boom. There we go. Boom. Clear section. Sorry about that. All right. So next one, determine whether the path C, E3, B. So let's just draw it out instead of me reading it to you. Sorry. So starting at C. So C, we're going to go E3. And then we're going to go to B. And we're on there. So now we're going to go E2. So whoop, around. Awesome. And then we're going to go from B on E1. And then to A. And then we're going to go on E6. And then we're going to end up at C. So the question is that going to be a Euler circuit? All right, so we go back and look at the definition of an Euler circuit. An Euler circuit is, so first of all, we have circuit, which that means it starts and ends at the same spot. So check, we got that part. We definitely have a circuit. However, it's not an Euler path because an Euler path has to include each edge. And we didn't get each edge. So we have a circuit, but not a path. So therefore, it's not an Euler circuit. All right. So next one. Let's see. Find the degree of vertex A and B. So vertex A would be 1, 2, 3, and vertex B would be 1, 2, 3, 4. All right. And then the last question is, find an Euler path in the graph in figure 5. All right, so go ahead and hit pause for a second and play around with that. Remember, to be a path, you have to go across every edge without duplicating an edge, without crossing on it more than once. So we're not looking for a circuit, so you can start and end at different locations. We're just looking for a path. So go ahead and hit pause and see what you come up with. All right, so welcome back. So I'm going to start at A, and I'm going to go on E1. And then over to B, and then I'm going to cruise around E2, and then I'm going to cruise down E3 to C, and then I'm going to cruise on E4 to D, and then I'm going to cruise on E5 to A, and then down E6, and so there I have my path. So I would list that out as being A, E1, to B, to E2, to B, to E3, to C, to E4, to D, to E5, to A, to E6, to C. Sorry about that. And so that would be my listing of my Euler path for this particular problem. All right, so example 4, take a look at this guy. And that's the one we just did, sorry about that. All right, so then we throw in some more theorems for us to kind of think about. So whether you have access to a printer, sorry about that, whether you have access to a printer or whether you want to write these down, I think these would behoove you to have in your notes, because what they're basically doing for us is they're giving us the foundational ideas for us to keep track of. And so that way, if we're doing any particular problems, you kind of think about it and try to apply the theorems. I've kind of just been like trial and error in it to explain the vocabulary and so forth. So let's take a look and see what we have left. So then we have a quick conversation about Hamilton. So Hamilton was, once again, I won't read this all to you, but he was the most noted Irish scientist, mathematician of his century. So he came up with this idea of a Hamilton path. It's a path that includes each vertex of the graph exactly once. So he wasn't about edges, he was about vertices. So Euler was about edges, Hamilton was about vertices. And so a Hamilton circuit would include each vertex exactly once. And you have to end up at the initial and the final are exactly the same. All right. So then he added some questions that he asked. And so we're not going to explore that, but just remember the difference between the two is Euler is edges and Hamilton is vertices. All right. That wraps up videos for section 4.2.